Okay, so now we come to this classification, and now the need some space. Let's see which equations are not needed. Oh, now these are just variations. Why can't we move back? So, we already use all these as variations. Done with all this. Move the screen over here. Okay. Now the separation in different mode. So one obvious mode is one obvious separation, because the right hand side and this and that equation involve both E sub c and B sub c. So and the equations are linear. So wave equations are linear. These two equations are linear. So we can separate into two cases. One is EC is 0, the other is BC is 0. And in both cases, the right-hand side is not totally 0. Because if EC is 0, you just forget this term and that term. You still have B sub c, right? You have B sub c on both sides. And likewise, B sub c is 0, you still have E sub c on the right-hand side. So it's, naturally, you can separate the two cases. And let's see what's Jackson. Jackson, the first is B sub c is 0. So when you have B sub c is 0, which means the B total is just B sub t. There's no z component. And so B sub t is transverse mode. So it means the magnetic field is in the transverse direction. This is called the TM mode, transverse magnetic mode. Okay, and for this case, because BZ is 0, so you don't have EZ 0, so EZ is non-zero. Non-zero. Right. Now we can figure out the boundary condition for E sub c, right? Because sometimes E sub c is parallel to the conductor, parallel to the wall, always parallel to the wall, right? Because so this is cylindrical waveguide along Z. So EC is part of the parallel component. Part of the E parallel, right? Because E parallel has two components. So E parallel means on the conductor. So EC one component is on EC, the other is going around, because this is cross section. Even it's a transfer, but then there's one component is along the conductor. So that's also E parallel. But EC is obviously totally parallel. But the E parallel is 0 for a perfect conductor. If you can look back the figure, we did that last time. So figure 8.1. So E parallel is 0. You can look at E point. That's for perfect conductor. For finite conductance, is 8.2. Finite but small finite but large conductance is 8.2. Figure 8.2. But E parallel is 0, so this is the boundary conditions. The boundary conditions, EZ on the surface is 0. I mean, EZ is not 0 interior, but on the surface, you require E sub c to be 0. So that's the boundary condition, and obviously you satisfy the same differential equation right here. So you're solving a differential equation of E sub c satisfy this equation for the E sub c component, but it's subject to the boundary condition. It's 0 on the surface. Okay, so that is what we call a Dirac boundary value problem. Okay, so that's the TM mode. Yeah, the other way around, so this is Tm. For Te mole, you have the E sub c is 0, E sub c is non-zero, so E is totally transverse, so we call that the transverse electric mole. This is a Te mole. So now BZ is not zero, so now you have a BZ along the Z direction. Now the boundary condition for this one is slightly more complicated. You actually need the equation that involving BZ, which is this, either this equation or this equation. It's basically the same. Doesn't matter, right? So there's a B sub C here that we need, but it's not simply set it to 0 because now the boundary condition. If you go back to the figure, so BZ is B parallel, but B parallel is, or H parallel is not necessarily 0 on the surface. Okay, so that we talk about on for 8.1, we should show that. But the H parallel is not 0, but H perpendicular is 0, or B perpendicular is 0, right? Or Bn. So perpendicular means along the n direction. So on this surface of the conductor, there's an n direction. There's the other direction is parallel direction. I mean, but they parallel in the transverse direction. Okay, so you use that. One thing you can do is doing a dot product between n of the whole equation, right? Because when you have the n dot into b sub t, you get the b sub n direction, b sub n, which is 0, which is what we call in figure 8.1 b perpendicular, right? H perpendicular or b perpendicular is 0. So you take take this n dot. N is the normal direction. N dot into the whole equation, right? So the n dot b sub t is 0. Now the second term is z cos into e sub t, and you want to n dot into that. And now for this one, you can use the cyclic rule because this is a dot product and you see the cross product, right? You can cycle it through, and so that should equals to, if you cycle it over, it equals to you know, what is easier, n dot n cos e sub t. Let's see what time about our time. So which one is easier? So you cycle it through, and cos e sub c is equals to, so this a dot b cos c, right? And then equals to b dot b is c, so c dot c cos a is et cos a. And then also this, the first one is et z dot into n cos c, n cos c. So this equals to this one. And now see what is reduced this one, n cos c. So this Z is in this direction, N is in the direction is in the transverse direction. Transverse direction has two directions. One is N, the other is perpendicular to N, also perpendicular to Z. So N cos Z is in that direction. But this direction is parallel to the conductor, parallel to the wall. So N cos Z is parallel to the wall. So this E dot into that will give you the E parallel. This one will give you a part of the E parallel. Right? But we already showed that E parallel is zero from the boundary condition consideration. So you have C N dot this one equals to this one, which is pick up the parallel E component. That one is also zero. So this will be zero. After you take the dot product, this is zero. This is zero. The right hand side is by N dot into this. N dot red T pick up the partial N direction. So this is partial BC partial N direction, but on the surface it's zero. Okay, this is T. T emo is this one, right? Okay, out of time, but then these are assuming one of them are non-zero. The third one is let's just give it a name, but discuss the property next time. The final case is when both BZ is zero, BZ is zero. From these two equations, both of these are zero. Obviously, you cannot use these two equations. But you can see the condition why if the numerator is zero at both equations, but you want to find E sub t and B sub t, what should the denominator be? No, it cannot be infinity. The numerator is zero. The condition for finite left hand side, the denominator also should be zero. So this is the case. This is the case that omega square epsilon mu minus k squared is zero. So this is the dispersion relation we saw before. That's exactly the vacuum. Not vacuum, the uniform medium dispersion relation. So basically, for this case, because both electric field and magnetic field transverse, it's called a TEM, transverse electromagnetic. Okay, but we'll talk about the property of this one. It's basically very similar to the uniform medium wave, plane wave, but it's not a plane wave because it's confined to the waveguide. But there's a restriction on the property of the waveguide. We'll talk about that next time. Okay. So we need to go back to the case when both EZ and BZ are zero. That's called the TEM mode. The reason is that what is possible is because both in the relationship between the transverse component and the Z components, 8.26, if both all the Z components are zero, the right hand side can be zero, but it can be found only with the denominator is zero. So basically, the denominator is zero, so we use epsilon omega square minus k squared zero. Okay, so the dispersion relation is exactly the same as the not vacuum, the uniform medium plane wave. You remember I think it's 7.1 or 7.2, so we divide the dispersion relation for vacuum. So that is fine. So that's TM. But then we cannot use 8.26 to get the transverse component because both the numerator and denominator are zero, so that cannot use the equations. So we need to go back to the equation 8.23 to 25 to get that. So in those equations now, all the right-hand side are 0, right? Because EC is 0, EC is 0. So what you get is, in this case, obviously the 8.25, we should, like 8.25, the second equation of that would automatically imply that curl of ET 0, and likewise 8.24, you get the curl of BT, and 8.25 will give you the two equation. 8.25 will give you divergence, transverse divergence of ET equals 0, and the transverse divergence of T equals 0. Okay, so that kind of straightforward. It's okay. So that and we actually have seen that in one homework problem. You remember one homework problem that the transverse, we actually show that the transverse electric field magnetic field satisfies the electrostatic equation. And you look at that, those are like electrostatic. Electrostatic, you have this curl E0, right? But in 3-dimension, in last semester, you learned that for static field, curl E0, because basically the Faraday is not a dBdt is 0, obviously, curl E0. And divergence E is not necessarily 0, but if the charge is 0, then divergence E is 0 also. So in this case, you can say if curl E is 0, then E is minus flat D of the potential phi. Just use this notation phi. We didn't talk about that. Doesn't matter. Never mind. It's still you can do that because a gradient, if curl of a gradient is always 0, so you do exactly the same trick as electrostatic. Make electrostatic potential, and then that solve this equation. Now divergence, transverse divergence is minus Laplacian. Transverse Laplacian of the scalar potential, that make it 0. Right? Then the problem becomes just solving the transverse Laplacian. Okay. I mean that Laplace equation, transverse Laplace equation. Okay. Another way to look at that is go back to 8.19. This 8.19 is transfer Laplacian, that's mu epsilon u square minus k square, and operate on all components. Okay, but for the TEM mode, we already said that this is the dispersion relation. Basically, this whole term is 0. The transverse Laplacian, any component is 0, and so if you write it a gradient, the transverse Laplacian of the phi is always 0. Okay, so that's another way to look at that. So that's the same as what you worked on in the homework problem. Okay, and then another similarity, you can look at again this the relation 8.23 or 24, because now you can relate E sub t and B sub t. The first, so 8.24 again. Other than this, the first equation will give you the partial z is just I times k, because we assume it's the ikz factor Okay, and then plus, okay, multiply by E sub t, I omega t cos E sub t equals to 0. The right hand side is 0. And likewise, this 8.24 will give you I E sub t minus I v epsilon equals E sub t 0. Right? And these relationships are exactly like the plane wave relating the the components of electric field and magnetic field for the wave, and that we derived it that in chapter 7 already, like this one solve piece of t here. Piece of t is just you move just to the other side, cancel I, and then you have mu k. So, so basically, E B sub t is also perpendicular to E sub t. And both E sub t and B sub t are perpendicular to the propagation direction, which is now C direction. And so they are transverse. So this is exactly the same as the plane wave relation. And you can also use this one is epsilon mu omega squared is k squared over omega. I mean, this is k squared, so you can substitute that into here. So that becomes k squared over omega squared. So this is k over omega squared. Omega squared. This omega, this should be, that's omega here. That's omega. This, k over omega, just k. Right. Okay, so that is the vacuum relation. Right. Do you remember we divided 7 point something, 7.1 or 2, the plane waves. All right. So basically, the TEM mode is like plane wave mode in uniform medium, except that it only exists over the region of interest. But then the region of interest is actually also restricted because of this electrostatic property. So, for example, this the geometry of this rectangular waveguide with just one cross section, like whatever we talked about last time, or whatever cross section. If it's the same along Z, so that's called cylindrical waveguide. But for this one, it actually does not support TM mode because over the cross section, we have we need to satisfy a Laplacian phi is 0. But you have like assume perfect conductor outside. Outside is perfect conductor. So the potential on the perfect conductor wall, you can set them to 0 also. If 0 is outside of the whole boundary, 0 outside on the surface, outer surface of the waveguide is all 0, then what should be the solution for phi? What should be the interior phi? What should that be? If this enclosed the whole volume, constant should be constant. What? Yeah, it's constant. What should be the constant value? If phi is 0 outside, what is the constant value? 0, yeah, it should be 0 because the solution is unique. But in I think in Jackson, chapter 1, we already divided that. The Laplace equation is unique. In that case, we actually use the 3D volume. but the same derivation applies for 2D also. You solve the 2D Laplace equation at the outward, it's all zero, then phi is zero, obviously it's a solution to a Laplacian. Phi is zero, but uniqueness theorem, that's the only solution. Okay, so if phi is zero everywhere, then obviously the electric field is zero or magnetic field is zero, so there's actually no mole inside. So there's no TEM mole with a geometry like that. So with just a hollow volume inside and surrounded by the perfect conductor. So then the geometry required for TEM mode to exist, you have at least two surfaces. The cross section at least have two surfaces. One possibility is the waveguide has some an inner surface also, inner conductor or conducting rod or whatever. So now the cross section becomes you go back to the cross section becomes something like a conductor outside, and then a conductor inside. Like then you can support the EM mode. Okay, so this is like the geometry of coaxial 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 cable or something like that. So, but this case, then you don't have to set all potential to zero. So you have maybe phi sub 1 inside, phi sub 2 outside. And they can be time varying, so because we are wave propagating. Right? But as long as they are not the same, then the interior phi doesn't have to be the same. Okay, so the gradient t doesn't need to be zero, so you have b sub t, and likewise you have b sub t. Okay, so you at least need two surfaces. And another way to propagate TEM mode is you have two wire, both wire conductor. Then within the space, it doesn't have to be an outer space. Maybe outer space to go to infinity, you can still support the TEM mode. So that's another way to have the TEM mode. So, all right. So the TMO is some, in some sense, it's like a plane wave, except that it has to be confined with some kind of volume within the at least two separate conducting surfaces. Okay.